Hi everybody. Today we'll be going over the design philosophy and approach for implementing an RF via transition in a 14-layer PCB for mmWave applications, in this case on the lower bound of that spectrum at 30 gigahertz. So the original design intent for this was for a phased array application for satellite communications, and this is the goal is to essentially get a coplanar waveguide structure transition down into a stripline structure with adequate match and insertion loss and some other metrics. And this will be going over kind of the high-level implementation of doing this in a combo of software, including HFSS and Keysight ADS, and also I guess Excel is included at some point. So right here, this is showing the kind of the end result, but I'm going to step back first and show how to break this apart and how to do it in different sections in order to realize this in a more, efficient or practical manner. So a few things you can see here, like I mentioned earlier. There's the CPW, there's a strip line, there's a matching network here. But before we even get to that, one thing that we'll talk about is, in HFSS at least, there's a lot of benefit in creating your design stack up within HFSS. So that's something I typically do before any other step. And in this case, like I said, it was a 14-layer PCB. And, I prefer to parameterize everything here, whether it be the coupon size. Coupon is what I'm calling the kind of like the puck here, or the sample of the PCB. And also have everything else, including the copper layers and the core thickness and the pre-preg thickness, to all be given a variable so that can be adjustable moving forward. And you could even step back one step further, and whether you're doing this in Altium or whatever your PCB layout software is, there in this case I just use Excel. There's a lot of benefit in creating this PCB stack up, so you can visualize it a little bit better and use it for reference in your design. And in this case, I like to write my the reference, or what I'm calling this in HFSS, what the utility is for that layer. So what I'll be showing today is, out of this 14-layer PCB, I'll be working on a layer that's here. It's layer 7, or TX2. This PCB had multiple transmit and receive layers. In our case, transmit was at 30 gigahertz, receive was at a lower frequency. It also includes the various, like the dissipation factor and dielectric constant that are associated with each prepreg and core material. And one other thing to pay special attention to, especially in mmWave designs, is the types of vias that you're able to use. In this case, we're using what's called like a micro via, or every layer interconnect, or ELIC technology. And what that lets you do is essentially create these 2-layer vias that can go in any section of your PCB, and you're not having to rely on a through via, or you can essentially realize any sort of buried via or blind via or through via if you want, and you do not need to incorporate back drills into your design. And back drills, sometimes they're useful. It definitely helps you realize a cheaper design, or cheaper via type, but they do have some impact on your performance. But that's not the topic of this video. But I'm just pointing out here that the stack laser vias that we're using, what you're wanting to know as the designer is essentially you're wanting to know the via depth, the via drill diameter, and basically the annular ring, or the keep out copper pad around the via. In addition to that, you're looking to have the minimum trace size in mind. Basically, you can call it trace in space. So minimum trace size, minimum spacing from other features, as well as hole to copper clearance is another important metric to keep in mind in your design, because you're wanting to design something that's realizable and manufacturable. Otherwise, you'll send this out to a board house and they'll get back to you and say that none of this can be built, or at least none of this can be built with reasonable yield. And that just leads to another design cycle and wasted time. So that's just the high level on this PCB stack up. And once again, I'm putting this into HFSS and kind of using that as my core, or kind of like my blank slate of a stack up that I will then design into or design on. So moving forward from there, we have these two different components. One is the coplanar waveguide. The other is a stripline. You can see as the standalone core components. Initially, I would be designing the coplanar waveguide, and this is relatively straightforward. Ultimately, you're looking to design for a certain port impedance or structure impedance, and have it designed within your DRC or DFM rules, which were pointed out in that spreadsheet I just showed about a minute ago. I don't know if I'll necessarily go through all of the details in HFSS and how to do this, but for something like a CPW, you can, I before this I copied in the stackup and I deleted all the layers except for the top two. So you can see it's just layer 1 and layer 2 with a pre-preg layer in between. And one other thing to note is these wave ports here on port 1 and port 2. What that's, the thing to keep in mind for that is the width and height of your wave port. I know HFSS and Ansys do provide guidance on this, but the rule of thumb I use is sizing those to be approximately eight times your CPW signal line, transmission line width, and 8 to 10 times your pre-preg or substrate height, which you can see here this parameterized. Well, it's each of those are sized, the port width and port height, by a factor of 10 relative to that design metric. And something like this, there are good tools online that can be used. Even I know ADS has a tool as well, and some online tools to get to a rough port impedance of 50 ohms. And from there, in terms of boundary conditions and everything, you can get away with using like a radiation boundary. In this case, that you shouldn't, for having such a small structure, you shouldn't be having any resonance issues or radiation issues. At least for an electrically small structure. And other things to note for my setup, my simulation setup. In this case, I like to do a broadband sweep, and although my design is from 20 to 30 gigahertz, I am sweeping a little bit above that, so 15 to 35 gigahertz. And because of that, I'm solving at the highest frequency of my solution, which is 35. Now, this is something that would change if you're doing an antenna design or something that has more resonant properties or features. But in this case, it's you can essentially set your solution frequency to the upper bound of your sweep frequency. In addition to that, I'm ensuring that out of the changes I'm making relative to the default settings are reducing the maximum delta S, increasing the number of passes just in case there is some convergence issue, which isn't the case for this one, but just in case. In addition to that, increasing the number of minimum converged passes from 1 to 2. There, I am implementing a frequency sweep. Like I mentioned, it's from 15 to 35 gigahertz, and I have a fast sweep type, which I believe it's also a form of an interpolating sweep, and it has frequency steps of 1 gigahertz. And so you can have an initial design worked out in terms of the relative trace width and spacing and your via spacing. And what I'm showing here is this would be a via with some given radius, and then this is sort of like the via pad or the annular ring. And you can see it's butted up right against the kind of the edge of your copper ground port. So this is something you may need to give some padding to or margin to based on your fab house. Some fab houses will put in these vias, and then this ground pad will be etched back, and your vias will actually be kind of sticking out in your ground pad. But these are all things that you can, if you want to see how it affects your performance, you can always run optometric sweeps on various properties like trace width, ground spacing, via spacing, things like that. And it's helpful if there's within PCB fabrication houses and manufacturing, there's standards like IPC class 2 and class 3 that essentially sets the maximum deviation you can see, or the range of, for example, a trace width that you can see. I believe it's around 20% variation is allowed per this standard. So it's good to do these parametric sweeps within your design to ensure that what you're building or what you're designing can be built with some tolerance to it. And this is already solved. Actually, before I get to the solution, I will give a heads up that on, if we're looking at where the port is right here, you can see that there's two vias that are kind of cut in half, and they're combining the top and bottom ground layer here. And that is actually, it's necessary for when you're solving with a wave port, because it ensures that the potential on your top and bottom ground are identical. And in this case, we're using PEC. We're not solving with any sort of copper or different platings, or things like ENIG plating with nickel and a gold stack up or anything like that. But this is necessary. Otherwise, the risk that you have is it will solve the structure sort of like a parallel plate structure, and you'll be getting this different mode relative to that pseudo TEM mode that you're looking to achieve with a coplanar waveguide. So that is one thing to note, is to always ensure that you're kind of putting your ground potential to be identical on your top and bottom grounds if you're creating a CPW structure that looks like this. So that's the extent of the coplanar waveguide design. And you can see here, I think I was doing a sweep here earlier, but you can see the relative return loss and insertion loss for in this case, a 200 mil long structure, and also the port Z0 that we're getting here. So one thing to keep in mind with plots like return loss and insertion loss, these metrics are all defined relative to your normalization impedance. So in this case, we're normalizing all of our modes, or all the solutions modes, to 50 ohms because that's the system impedance we're looking to design around. However, if you're designing to 40 ohms, or your system impedance for whatever reason is 40 ohms or 60 ohms or 10 ohms, you'll be needing to change this renormalization impedance to actually determine the performance in your system. And likewise with the port Z0, if you're looking for the actual port impedance, you're wanting to unclick that renormalize all modes. And in this case, it shows that our port impedance is almost right on 50 ohms, it's 50.6 ohms. But if you do not check that, you can, if you do check renormalize all modes, you can make this whatever you want. So I can set this to be 48 ohms, and it looks like 48, which isn't the reality of the structure that you're creating. So that's just something to keep in mind when designing. So I believe that's the extent of the CPW. We're going to move forward now and just show the stripline structure that's being designed, which it's a very similar design process, where this is just a cutout of that 14-layer board. It's using, in this case, I believe, layers 6, 7, and 8, where 6 and 8 are the ground pores, and 7 is the signal layer, which also has a ground pore in it. So you can see there's nothing drastically different. Things of note will be, that signal layer will typically, in most applications, have, you'll have a signal here, as you can see by this little box here. However, most applications, there will be a ground pore, adjacent to that, within that signal layer. And one thing people forget or may not realize is, in this case, we have a pre-preg layer and then a core dielectric underneath. The pre-preg it's ultimately like this, lack of a better word, like a GUI, or this kind of this gelatinous, like resin-filled substance that gets heated and kind of baked and hardens after during manufacturing. But because of that, when you're setting down your pre-preg, it will fill in any voids that it encounters. And because it fills in those voids, there's a few things that will happen. Well, one is that the pre-preg will now, that pre-preg is now included in your signal layer, and that's something that needs to be accounted for in your design. It's not just going to be air or a vacuum, on either side of your signal. In addition to that, as it fills in, the effective thickness of that prepreg layer will be decreasing because some of that prepreg is going to different layers or filling different holes, and the material is just going to a different layer of existence at that point. But that being said, there's not much difference in designing this versus CPW. You are wanting to be careful with your port backing, your wave port backing, to ensure that the top and bottom ground planes are once again connected. In this case, the middle ground plane. But other than that, there's nothing drastically different that needs to be done here. I'm also using a radiation boundary here. Because it's very unlikely that there'll be any leakage or resonance or anything in the structure. And with that being said, these designs did have. You can see it's decent performance in terms of return loss. We're getting about 30 dB across the full band here. Keep in mind we're using this at 30 gigahertz for this video, and insertion loss likewise it's nothing too crazy. And then you'll see I did run a parametric sweep here to see how my port impedance or characteristic impedance of my line would be changing with different tolerance things, such as the stripline gap or the stripline width. And the nominal design here was actually not 50 ohms. It was, I believe, around 45 or 46 ohms, and that was for kind of for the application here. We're looking to reuse the same stripline structure for all of our RF layers, not having to have all these unique stripline layers that needed to be accounted for and supervised and managed. It just made things easier from a layout perspective to set the same design rules for every layer, for every stripline layer, that is. So, this is why you're seeing the performance is not dead on 50 ohms. It's somewhere around 45 ohms nominally. So, from there, we have the two building blocks here. We have the stripline and we have the CPW design, and next we're looking to match those together. So this shows a very high level design that uses all the stack-up layers from before, so all 14 layers, and it combines the designed CPW dimensions with the designed stripline layer dimensions. And so what has to go in between here now is it has to be some sort of via transition or some conductive transition. And in my case, what I mentioned earlier with the stack up and the via types, we're using laser like stack vias or stack micro vias. And this lets you very easily, within some manufacturing limit, put these micro vias on top of each other, maybe 5 or 6 times maximum, and go directly from the layer A to layer B. So in this case, CPW to the stripline. If you're not able to use this, you're going to have, probably if you're using like a through V or anything, there's the technology called back drills. And let me just get rid of this for a second. With a back drill, that essentially could be a through via or another type of buried via, where there's a physical drill that comes up from the bottom, drills out part of that stub, and leaves you with a structure that looks similar, but there may be a little tail or stub on the bottom of your transition. In our case, that was something we couldn't do because it was detrimental to performance. So we fortunately were able to design without that, but it is a possibility depending on the fab house you use, or also how much money are you looking to spend on manufacturing. So, in this transition, we're looking to go from essentially 50 ohms to 50 ohms, or needing to do that, in a manner that doesn't eat too much of our signal or impact our performance. So, inherently, you're wanting to design some sort of transition that looks like 50 ohms. And in this case, you have your signal right here, and in addition to your signal, you do have these. If I can get rid of this for a second. In addition to your signal, you do have via pads on each of your layers in between the top and bottom layer. This is something that I would recommend modeling, because otherwise, it does introduce kind of like this low impedance discontinuity, or this periodic low impedance. which ultimately will impact your performance of your transition. But regardless, you're looking to design this transition, and something with hopefully a 50 ohm impedance in that structure. So one way to do this, it's rather straightforward, is to create a coaxial structure that surrounds this signal via. So if we look at it from above, you can see this is your signal, and it kind of looks like a cross section on a PCB already. But you can't just have that signal via, because otherwise you have no ground. That signal is then able to leak out, or it could radiate, or it could resonate within your PCB, which is not something you're looking to do. Or maybe it is, but in this case we're not. There are some details that I'll gloss over here, but one thing, in order to design that coaxial structure, you can't have a perfect PEC wall, of course, but instead you can realize this in the form of a kind of like a ground via shield. And I'm showing this at a few different angles, but from the top, it kind of looks like that outer diameter of your coax. And from the side, you can see where this is going. And, thankfully we have the luxury of using micro vias and also, buried vias and blind vias here. So we can design a very compact and tightly confined ground shield around this signal via. And, you can see, it prevents any leakage happening towards the back of the stripline layer. It's preventing leakage on the side. We have a continuous ground port. We have a continuous ground port here underneath, so we're not worrying about any leakage to the bottom half of the PCB. And additionally, we have this ground via here, which is preventing any sort of like forward or front-facing leakage up in this area. So the spacing, or the effective diameter of this relative to the center, is something that can be designed as like a parametric. You can make that parametric and sweep the spacing, see what's feasible. Often you're working within the constraints of DRC and DFM, where these vias can't be super close from like a hole to copper clearance perspective. Also, you're looking to have some tolerance that, like I was talking about earlier, some tolerance where this doesn't have to be spot on every single time to have good performance. These vias here, we're going to ignore for the time being, but they're just ground vias, which will be used. Or you can think of it in a real design. This trace won't exist in isolation. So there's going to be other things near it. There's going to be other signals, other traces that you're probably not looking to couple to. So we can just think of this as random shielding vias that are on your PCB. And in addition, one more tuning knob you do have, in addition to the ground via spacing, is the copper keep out region, or the copper on your inner layers, the amount of copper, the diameter of the copper that you're removing as you transition down from this top to bottom layer, or layer 7 in this case. But this is very important to, once again, keep in mind you need these via pads on each layer in a micro via case. This might not necessarily be true for a through via, but for micro vias, stack micro vias, you are needing to model, or at least keep in mind that this exists. So I'll show here, this is basically the first pass out of the design. And what we can see is that the insertion loss or return loss is still not great. We're getting about, this is about 12 dB return loss at 30 gigahertz, which is our design frequency. At our non-design frequency, receive band, it's 16, which isn't bad, but we're looking to really improve this match here. And you can also see the return loss, if I can bring this up to 30 gigahertz. For such a small transition, this isn't great, 0.3 dB. And keep in mind, in reality, you will have much higher loss if you're not accurately modeling the metals that are being used. So I think here we're just using either copper or PEC, but in reality, if you have something like an ENIG stackup, that nickel introduces a significant amount of loss that isn't shown here, isn't accounted for here. And modeling that is beyond the scope of this video, but it is rather tricky. It's one of those things you may be better off just building and testing and validating that way. So from here, we have this performance. This is showing the return loss, or S11, of that transition. and it's looking at it from the perspective of the CPW line. So we would like to improve the performance here, and the way you can do that is some sort of matching network, of course. So, and one knob here, this is a kind of a trick that you can use in HFSS. You can change the de-embedding distance of your port to so I can show it better here. So if we have a port right here, we can de-embed this port by some length to see what the impedance looks like at that de-embedded plane. And that's useful because ultimately, we want to design a matching network, but maybe not something that far away. Maybe we're wanting to make it more compact, or as close to the transition as possible to eliminate any chance of it being affected by anything else in the design that we're not accounting for. So what I'm showing here is the input loss or return loss for a port that's de-embedded rather close to that transition. In this case, it's de-embedded by, I think, 75 mils. And it's showing the impedance at 30 gigahertz. So the one thing we can do is show the admittance grid and say, hey, that actually looks pretty close to this circle here on your admittance chart. So where I'm going to take this is something you can do in HFSS or whatever other solver you want, or manually by hand. But I'm going to generate an S parameter file here and then load it into HFSS and try to do a matching network from there. So here's my S parameter file, and based off where I'm seeing this impedance on the admittance chart, I have two tuning knobs. I can change my electrical length from that transition, which is essentially like a pseudo de-embedding. So in this case, you can make it negative to pull it further away, or add length to put it closer to the port. And additionally, I think I can realize this matching network with a shunt stub, or shunt open stub. So I'm going to gloss over the tweaking component of it. But essentially, I'm taking this existing performance that we have, which I will show here, right here, and I'm applying a matching network to it in CPW. And you can see this is after some playing around with it. I am able to, before, recall this performance was, I believe, around 12 dB of return loss. And now you can see with just a simple stub matching network, you can get somewhere around at 29 or 30 gigahertz, you can get under 25 dB match for sure. So this is obviously, it's an improvement relative to what we had without the matching network. So now that we have a rough design, and this is kind of showing the values that were used. So, a 26 degree stub, and this is kind of like a minus 5 degree. So this is the de-embedding tuning knob you have. So going back to HFSS, in terms of how do we realize this, we have the same structure as I showed previously a few minutes ago, but my stub matching network is going, I realized it in this kind of swept curved stub that follows the form factor of that via transition, or that coax structure. And that was done for the sake of keeping it as compact as possible for my application. So one easy way to do this in HFSS is to create kind of like a polyline. So you would create just a line right here, like you just in your I guess on your XY plane, you create a very small line, and then you would sweep that line around an axis. And this line I'm setting to be a 50 ohm. It's 50 ohm CPW width, and then I'm sweeping it with a variable, which I believe I hear him calling stub angle degree, and that is setting the angle relative to, I guess we're using a right-handed coordinate system here. So this is currently swept to be 80 degrees, which in this case equates to roughly the electrical length that was designed in the AES, 26 degrees. So this gives you an effective electrical length of roughly 26 degrees using this stub angle degree parameter. And additionally, from there, I have a variable for stub offset x here. And what that is the distance of the center of the stub to the via transition. And that lets you, you can essentially move this up and down. And I think I can show it here. So I made it 22, so you saw it further away there. If I bring it back to 18, you see it come back closer to the via transition. And same with the stub angle of degree. If I make it 40 degrees, you can see it shrinks like this. If I make it back to 80 degrees, you're seeing the original design. So, there's some iteration here. Your initial design may not be correct, and that's why this parametric component is so valuable, because it lets you change where the stub matching network happens in your board. And so there were a few trials and iterations that were needed to get to this point. But ultimately, with this stub matching network, you can see, this is the original design I was talking about. It's around 12 dB. If I go and introduce the stub match for comparison, we can see we were able to improve the design from around 12 dB at 30 gigahertz to 26 dB at 30 gigahertz. And that matches pretty closely with the ADS simulation that was done, which was ultimately using realized components with no loss or anything like that. So this is a little bit more realistic. Instead of like 30 dB, we're getting about 26 dB of maximum return loss. And likewise for the insertion loss, what I'm showing here, let's see. What I'm showing here was the original design, so that's 0.3 or 0.4 dB of insertion loss. But with that matching network added, we're getting under 0.1 dB, which of course will actually be just 0.05 dB, most likely not because of manufacturing reasons or copper losses and things like that. But this is a very good sign as to where the at least the general design health of the design. And of course, this is something that you're really wanting to do a parametric sweep on in terms of your stub dimensions and things like that to see if how sensitive it is to manufacturing tolerance, similar to what was done in the CPW and stripline designs. But yeah, it's show here then on the Smith chart just for going full circle here. See our original design and then our new design with that stub matching network. And you can also, if you're interested in the chance of anything radiating or coupling, you can always visualize it looking at surface currents or electric field in that area. And here I have both overlaid, so it's a little bit chaotic. They have two different color schemes or heat maps, but you can see sort of where these E fields are going, or what the E fields look like in the structure. In addition to the surface current. So the surface current is on the conductor itself, and the E fields are within the substrate or in free space here. And one thing I would recommend is setting the dynamic range of your fields to be reasonable. So for the E field here, you can set the scale and specify your limits, or you can either specify the limits or you can auto scale it and limit the precision of your auto scale. And what this equates to is a 2-digit limit. You can see the dynamic range of your fields to be 2 times 20 dB, or the number of digits times 20 dB. So in this case, we have 2 digits. You multiply that by 20. You have 40 dB of precision here. So you're seeing this 40 dB range. If I were to set that to 1, we're seeing 1 times 20 dB of range. So it's something to keep in mind when you're looking to do visualizations, because if you do it to 5 dB, that's 100 dB of dynamic range or of range here, which makes it look like this thing is spewing out fields. And maybe you are looking for 100 dB of isolation, but in most applications that's not the case, and you're looking for 40 or 60 dB is more than good enough. So that's one thing to keep in mind. But yes, otherwise that concludes sort of the high-level design philosophy of how to go from CPW to stripline and putting that via transition with matching network in between. And here you can see once again there's the stub match here, so showing the fields around it, which is pretty cool. But yeah, I hope this video was informative, and hopefully I don't take 6 years to record the next video. You can do some other cool designs and tutorials moving forward. Thanks, guys.